Ladies and gentlemen, Dr. Peyam.
Hi, thanks for coming, and today we will evaluate the integral of 1 over x to the 4th plus 1 dx from 0 to infinity. And I invite you all to look at Black Pen's Red Pen's video where he did it by finding an explicit antiderivative. But here we will not find the antiderivative, yet we will still find the integral. And so life is complex, so let's do some complex analysis. Ooh. So here's the idea. Instead of evaluating 1 over x to the 4th plus 1 dx, we will evaluate the complex version of it. Integral of 1 of z to the 4th plus 1 dz over some curve c. So where c is a suitable curve, is a clever curve in the complex plane. So it's very exciting. So as I said, we'll consider a function basically 1 over x to the 4th plus 1, but here z is a complex number instead of a real number. But it's still basically the same function. Actually, it's not the same function at all, because even though this one is defined for all points, there will be some points where this is undefined. So let's first of all look at the bad points of this function. So step 1, maybe step 0. It's not quite part of the proof, but let's figure out where the singularities of this function are. Look at the singularities of 1 over z to the 4th plus 1. And it's very interesting because usually in calculus you think of singularities as being bad points, like 1 over x equals to 0 are bad points. Here, they're actually, in complex analysis, they're actually good points because they will actually help us to evaluate integrals. So it's very counterintuitive, but hey, this is complex analysis, so nothing is intuitive. Okay, so where are the singularities? Well, it's precisely at the points where this is undefined. So so singularity when z to the 4th plus 1 equals to 0, so z to the 4th equals to minus 1. And usually in the real case this has no solutions. Here actually it has basically 4 solutions here, because notice we can write minus 1 as e to the I pi, but also minus 1 as e to the minus I pi. So z to the 4th, since z to the 4th equals to e to the I pi, that basically gives us z is plus or minus, well, not even that. Basically the solutions are plus or minus this 2 over 4 and plus or minus this over 4. E to the I pi over 4 and plus or minus e to the minus I pi. Someone else can maybe do that, show that. The point is, this function has precisely 4 singularities, and they're kind of nicely arranged. They're arranged on a square. So the singularities are, so if you like, this is the complex plane. Okay, this is R and R. Okay, not R and C. Okay, so burn. Okay. Okay, so the singularities are on e to the I pi over 4, e to the minus I pi over 4, and the opposite of those two. So minus e to the I pi over 4. And minus e to the minus I pi over 4. Again, you can write it as 3 pi over 4 and 5 pi over 4, but it's enough for our purposes. So look how pretty this is. This is the complex Mona Lisa, because we have those four singularities arranged on the square. Okay, good. And now, as I said, we sort of want to find a nice curve, where on the one hand, this integral maybe becomes a real integral, 1 over x to the 4th plus 1, and it also swallows one of the singularities. Because there's a theorem that says, swallowing singularities is good. It's the Corsi theorem, I think. But there are actually many ways of doing this. One way is just to consider the semicircle that goes from here to here. It's nice because there are only two parts of the curves, but they have two singularities, and frankly today I'm a bit lazy with that. So let's just pick another curve, namely here, let's pick the quarter circle. And why is this nice? Because first of all, it swallows one singularity, so it's good, but also only one. And as I said, just a little bit work. And also, because it swallows this real axis, that contains part of the information that we want, and it turns out this is a little bit symmetric. And I guess the only downside is here we have to evaluate 3 curves instead of 2, but at least we just have to do one singularity. So. Okay, that's good. And now let's actually do this. So step 1. Okay. So fix R positive. And the idea is we will take R go to infinity and let CR be the following curve. So it consists of, first of all, this axis, the real axis going from 0 to R, so let's call this 1. It consists of this semicircle, this quarter circle, I guess let's call it 3. Again, just by order of this stuff we'll do it. And finally, it consists of this imaginary axis, let's call it 2. And again, this reason is I'll first do this part, and then this part. Or, wait, not even that. Yes. Okay, then what do we have? Well, because the curve consists of the 3 parts, the integral over that curve, z to the 4 plus 1 dz, that equals to the integral of the first part, 1 over z to the 4 plus 1 dz. It makes me feel very dizzy, dz. Okay, and then integral over the second part of the curve, 1 over z to the 4th plus 1 dz, plus the integral over the quarter circle, 1 over z to the 4th plus 1 dz. You can guess, we will calculate this integral, this integral, this integral, and then we'll calculate this integral. So first part, actually the easiest, but the most relevant one, because part of our answer will be there. So let's just remind ourselves, maybe ironically, how to evaluate complex integrals over curves. All you have to do is parameterize the curve. So, first of all, as I said, we consider the first curve. 2 is the study of 1. Well, what is this curve here? It goes from 0 to R on the real axis. So we can parameterize it by phi of t equals to t equals to t. So at every point t, you have the point literally t plus 0i. It's important to understand here t is a real variable, and here we have the complex number, if you like, t plus 0i, and t goes from 0 to r. And then what do we have? It turns out there's this formula that says 1 over z to the 4th plus 1 dz. Well, it's the integral from 0 to r of 1 over the value of z on that curve, phi of t to the 4th plus 1, phi prime of t dt. And that's because if you want, it follows from dz equals to dz over dt, dt But dz is just the curve gamma, that's phi prime of t dt. That's maybe a heuristic way of understanding this. But look, phi of t equals to t, so the derivative is just 1. So in the end, we have integral from 0 to r, 1 over t to the 4th plus 1 dt. But look, first of all, what happens when r goes to infinity? Well, when r goes to infinity, this in fact goes to the integral we want. Right? 1 over t to the 4th plus 1 dt. Because remember, in this case, t is a real variable. So we get the integral from 0 to infinity of this function. So that's actually our answer. And of course, we want to figure out what our answer equals to. And so let's continue. Let's, study 2. So step 2. Okay, so what is this curve here? Remember, it goes from up to down. So if you like, it goes from the point Ri to 0. Because remember, here we are on the imaginary axis. And well, one way to parameterize this is just phi of t. You start with Ri. And then because you're going down with the imaginary axis, you just add minus it. And notice it precisely at time t equals to r. So if like this becomes t equals to 0, at t equals to r, you get ri minus ir, which is 0. So we're good. And that's one thing. And then we also need to figure out the derivative. It's minus I. So it's just both ingredients we'll need. 1 over z to the 4th plus 1 dz. That's integral from 0 to r of 1 over minus it to the 4th. Wait,
no,
ri minus I. Huh?
Ri minus it.
Yeah, ri minus it. Yeah. Okay, 1 over ri minus it to the 4th, okay, plus 1, and then minus I, so phi prime of t, so minus I dt. So that's phi prime of t, but then one thing you can do is you can just take, okay, no problem. First of all, from this ri minus it to the 4th, you can factor out the I, so r minus t to the 4th, and so you get I to the 4th, r minus t to the 4th, so you get r minus t to the 4th. So in the end, you have minus I integral from 0 to r 1 over r minus t to the 4th plus 1 dt. And well, let's just use a quick change of variables. So I guess that u dr minus t du equals to minus t minus dt. So dt equals to minus du, and this goes from r to 0, 1 over t to the 4th plus 1, minus dt. But well, if you switch it, you get minus I times minus 1 times minus 1, 0 to r, 1 over t to the 4th plus 1 dt. This cancels out, and you get a minus I. integral from 0 to r, 1 over t to the 4th plus 1 dt. Well, look at that. Now let's let r goes to infinity. And we get minus I integral from 0 to infinity 1 over t to the 4th plus 1 dt. Wait, that's great. That's actually minus I times our answer. It's actually sort of good news because, on the first part we have our answer. On the second part we have minus I times our answer. So somehow in the end we get an equation involving our answer and then we can solve for it. Okay, that was step 2. Actually, here's a funny story. On my notes I made a mistake. Actually 2 sign mistakes, but they happen to cancel each other out. That's why it actually works nice in the end. Okay. Again, life is good as long as you make an even number of sign mistakes. Just to make an odd numbered one, it's not good. Okay. So those were the 2 curves, but remember there was this evil quarter circle. I keep saying semicircle, but it turns out what I want to show is that the semicircle actually doesn't really matter. So step 3, study of 3. And remember, we're just integrating it now here from this circle to this circle. So this is R. And this is Ri, so on this circle, and what I want to show is, actually the integral of this circle just goes to 0, as r goes to infinity. Goal, show the integral over the circle of 1 over z to the 4th plus 1 dz goes to 0 as r goes to infinity. And, well, the best way of showing something goes to 0 is showing that the absolute value goes to 0. So let's just do this. It's inequality time. So 1 over z to the 4th plus 1 dz, well, it's less than or equal to, by triangle inequality, 1 over absolute value of z to the 4th plus 1 dz. And don't make the mistake I made. I thought, well, this is a positive quantity, so we can remove the absolute values. But careful, it's complex, so we can't do that. However, there is this nice thing. So absolute value of z to the 4th plus 1 is equal to z to the 4th minus 1. And here's the intuition. We want to show this is smaller than something. The whole thing, 1 over this, is smaller than something. So we have to show that this is bigger than something. And there's just one inequality, really, that says something is bigger than something else. It's this, not the triangle inequality, it's the anti-triangle inequality, if you want, that says a minus b is greater or equal to absolute value of a minus absolute value of b. So in other words, if we apply this, we get absolute value of z to the 4th. Is this junk is greater or equal to absolute value of z to the 4th minus absolute value of minus 1. So that's z to the 4th minus 1. But remember, we are on this semicircle of radius r. So whatever z we have here, its modulus will be r. So this is r to the 4th minus 1. So putting everything together, z to the 4th plus 1 is greater or equal to r to the 4th minus 1. So 1 over z to the 4th plus 1 is less than or equal to 1 over r to the 4th minus 1. So our integral, this chunk here, is less than or equal to integral over 3 of 1 over r to the 4th minus 1 dz. And here's a cool thing. This does not depend on, z anymore. dramatic silence. I know it's like in the jungle. It's like, watch this flower unfold. Watch this integral being evaluated. Okay, so, but here's the nice thing, this integral does not depend on z, so we can take this r junk out, and then we get integral over 1 dz. But this is a line integral, so the value of the integral is just the length of this quarter circle, which is 1/4 pi to 1/4 times 2 pi r, so pi r over 2. Pi r over 2, and that's pi over 2 r over r to the 4th minus 1. And well, if r goes to infinity, this is like r to the 4th, this is like r, so it's r over r to the 4th, 1 over r cubed, and that goes to 0 as r goes to infinity. Which is good news. So the bad, in other words, the enemy, the bad term that we want, goes to 0. So, so what we have on the left-hand side, so maybe a summary. Summary, we have that, our integral z to the 4th plus 1 equals to 1 plus 2 plus 3. Well, that equals to our answer plus, it's minus I times the answer plus 0 as r goes to infinity. And so that's equal to 1 minus I times our answer. But of course, the next step is actually to figure out what is this junk. You might be confused, so that's what you might be feeling now. But it turns out that it's actually easy to calculate the integral over the whole thing. So here we calculated the pieces, but remember, there was this singularity, and we haven't really talked about the singularity. But now let's do it. Let's discuss the elephant in this room, or as in complex analysis we say, let's discuss the singularity in our region. Step 4. The actual study of this thing. As I said, it turns out it's very easy to calculate this. Namely, there's a theorem, and it is called Corsi's theorem, that says that this integral is actually basically equal to a factor times the residue at this point. It's equal to 2 pi I times the residue of 1 over z to the 4th plus 1 e to the I pi over 4. And I'm not going to go too much into the details of this, but this is a number that actually tells us how good or bad this function behaves near the singularity. And by the way, if you had 2 singularities, you would add up 2 residues. That's why I made the work a bit simpler by just calculating 1 residue. But it turns out there's actually a very nice formula for that residue. It's called the limit. You can calculate this. Again, by some complex analysis, you can calculate it to be the limit as z goes to the singularity of z minus your singularity over your function. But here's the cool thing. So this is a complex limit, yet you can still apply L'Hopital's rule for this. So L'Hopital extends to complex numbers. Okay. So if you calculate equals to the limit, if you want, as z goes to ei pi over 4 of 1 over 4z cubed. But look, this does not have a singularity at this point anymore. So we can literally just evaluate this. So it's 2 pi I over 1 over 4 e 3 pi I over 4. So ei pi over 4 raised to the third power. And you can simplify this to be pi I over 2 e to the minus 3 pi I over 4. Well, what is this number? It corresponds to the angle minus 3/4 pi. So maybe somewhere over here. And, well, this corresponds, if you like, in the unit circle, it corresponds to the point minus square root of 2 over 2 minus I square root of 2 over 2. So the point is, our answer is pi I over 2 times that. Okay. Almost done, so. Oh, let's keep the summary, it's very good. So it equals to pi I over 2 minus square root of 2 over 2 minus I square root of 2 over 2. And that, if you want to simplify it, you get minus square root of 2 over 4 pi I times 1 plus I. And there's a reason I write it this way, because we can simplify it a little bit. And so, what do we have? Now here's our grand finale. Remember what we had, the integral that we wanted to evaluate is 1 minus I times our answer, but this integral is actually equal to that. So, in other words, all we have to do is solve for this equation, whatever junk we found, minus square root 2 over 4 pi I times 1 plus I equals to 1 minus I times our answer. And therefore our answer is this monster divided by 1 minus I. So answer is minus square root of 2 over 4 pi I 1 plus I 1 minus I. But again, we don't like i's on the denominator. So let's use the complex conjugate for this. And so we get minus square root of 2 over 4 pi I. So this becomes 1 plus I squared. And it turns out this becomes very simplified. It's 1 squared plus 2I plus I squared. That's 1 plus 2I minus 1, and that's 2I. So the denominator is 2I. What about the numerator is 2I. What about the denominator? This is just 1 squared minus I squared. So that's 1 minus minus 1. That's 2. So 2I over 2. And then, well, look, it first looks like an imaginary answer, a negative, but it turns out because of this I and I, we get a minus 1 pi minus 1. This cancels out with this minus 1. So our answer is square root of 2 over 4 pi. Yay! And that's our answer. And usually I would write a box, but just in honors of today's picture, let's just write the quarter circle. We are done.
Nice.
Yay!
Woo.
Witness the power of complex analysis.
Nice.
Yeah.
How much do you like complex analysis?
It's so beautiful.
Wow.
It's like analysis heaven. Like you get tortured in analysis because there are all this stuff you can't do, and suddenly you can do it. You know.
Wow.
Going to Vegas or something.
Well, what are you going to do for your birthday, by the way?
Huh? Oh, a very, very special presentation, and basically it's a little surprise, but I'll do a very long integral, but with a nice surprise in the end.
Cool.
So
Be sure you guys check out his channel.
Woo!
And subscribe to
Yes,
both of the channels.
definitely.
Yay.